student, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of microwave radar, we are going to have discussion on Doppler effect and CW and MTI radar. So, continuing with the radar, what is the basically the radar problems and what are the basically its solution. So, basically one of the major problem arises in the operation of the radar, and for its solution the Doppler effect comes into existence. So, the first slide is based upon why Doppler effect in radar. Radar comes into existence in the scene during the Second World War, and in the real world what is happening to the radar? Radar has to deal with the two basic problems, that is the noise and echoes from the natural environment such as land, sea and weather, and they are called as the cumulative clutter. Cumulatively it is called as the clutter. So, main factors which comes into face which the radar has to face in the real world is, first one is the noise and the second one is the clutter. Clutter, sometimes the clutter echoes is more magnitude, having the more magnitude than the aircraft echo, or we can say that the target echoes. When an aircraft or the target echo and a clutter echo appear in the same radar resolution cell, the aircraft may not be detectable. Aircraft or the we can say that a target may not be detectable. So, this one is the most common and the most reliable, most important difficulties faced by the working of radar, that is the clutter. So, when the clutter magnitude is larger than the target echo, clutter echoes is larger than the target echoes, then in this case sometimes the target may not be detectable. For the detecting moving target in large clutter region is by making use of Doppler effect. So, for detecting the moving targets in the case of a large clutter region, we are using the Doppler effect, which is the change of frequency of the radar echo signal due to the relative velocity between the radar and the moving targets. So, why the Doppler effect comes into existence, get an answer, that is basically Doppler effect comes in the radar in the case of a region where the clutter echoes is large as compared to the moving targets, and the Doppler effect basically is the change of frequency of the radar echo signal due to the relative velocity between the radar and the moving target. So, when the relative velocity, not the static velocity, we are talking about the relative velocity between the radar and the moving target. So, frequency of the radar echo signal changes as per the relative velocity between the radar and the moving target. That means ki our radar moving target is coming closer to the radar or it is moving away from the radar. On that basis, the frequency of the radar echo signal changes. So, this type of effect is known as the Doppler effect. Now, the detailed description of the Doppler frequency shift. The Doppler effect is the effect that changes the frequency of the electromagnetic signal, or the echoes we can say, that propagates from the radar to the moving target and back to the radar. And what is responsible for that? The relative velocity change between the radar and the moving target. If the range to the target is r, and then the total number of wavelength lambda in a two-way path from the radar to the target and return is 2r upon lambda. That means it is the signal is going to from the radar to the moving target and it is coming back. That means if the r is the distance, the complete distances will be the 2r. So, if the range of the target is the r, then the total number of wavelength lambda in the two-way path from radar to the target is given by 2r by lambda. Each wavelength correspond to the phase change of 2 pi radian. Each wavelength correspond to a phase change of 2 pi by lambda. So, total phase change will be 2 pi into 2r upon lambda, because the wavelength will be for the two-way side, that is going from radar to the target and coming back to the radar again, is equal to 2r upon lambda, and for each wavelength the phase change will be 2 pi. So, in that case the total phase change in the two-way propagation is 2 pi into 2r by lambda, which is equal to 4 pi r upon lambda. If the target is in motion relative to the radar, the Doppler effect comes into existence for this particular case. The r is changing and so will be the phase. So, what will be happening? If the target is moving, what will happen? If the target is moving related to the radar, r is changing and correspondingly phase will change, because sometimes it happens that for first case, let us have a look. For the first case, the target is radar is here and the distance is target is here, which is as the target is moving. So, radar will remain at its position, but the distance between target here comes. In the third case, radar is here, target comes here. So, what we are saying that r value, which is the distance between radar and the target, is changing in as the target is moving. So, correspondingly our phi will also change, and always keep in mind that Doppler effect major impact we can see in the moving target only, and for detecting the moving target, the Doppler effect comes into existence in the case of a radar. Now, so differentiating what we have, differentiating equation 1 we have a phi value, that is total change in the phase in the two-way propagation, 2 pi r upon lambda. And why we are differentiating it? Because as a target is moving related to the radar, r is changing, our r is changing, and correspondingly our phi will also change. So, omega d is equal to d phi upon dt. We have differentiated the phase and denoted that with the omega d. So, when we are differentiating phi d by dt, so what is phi here? 4 pi r upon lambda. 4 pi r upon lambda. So, what is the changing? Wavelength is not changing. 4 pi is also a constant. So, what is the changing factor here? R. That is why 4 pi upon lambda is taken as a constant in the outside, and we have differentiated r with respect to t. So, when a distance is differentiated with the respect of time, the resultant will be velocity, and so we have the Vr. Vr is equal to dr upon dt, and a radial velocity, its unit is meter per second, at a rate of change of range with time, and velocity upon lambda is equal to our frequency. So, which is noted by Fd now. So, we are now have the angular rate of change of phase, which is equal to d phi upon dt, is the angular frequency among omega d, and it is equal to 2 pi Fd. How the Fd comes into existence? Vr upon lambda, that is velocity upon wavelength, which is equal to the frequency. Now, here comes the expression for angular frequency. Now, let us just look at this geometry of radar and the target in deriving the Doppler frequency shift. This is basically a antenna of the radar, and this picture is basically depicting the radar. This is our moving target, which is described in the terms of aircraft here. Range r, it is moving with the velocity v, but it is in the direction of the range, that is in the direction of the radar, it is making an angle theta. The moving target is making a angle theta with the direction of the signal which is coming from the radar. So, we have to deal with the velocity, that is equal to Vr, and it is equal to V cos theta. Since V is the velocity of the aircraft and theta is the angle which the direction of the movement of the moving targets makes with the direction of the radar. Now, the angle between the target velocity factor and the radar line of sight is theta, which we have seen that this is the direction of the radar line of sight and this is the direction of the moving, and this is the theta. So, Vr is the velocity which we have to consider, and that is in the direction of the our line of sight of the radar, and it is equal to V cos theta, where V is the speed of the magnitude of the vector velocity of the moving target. If the rate of change of phi with time is the angular frequency omega d is equal to 2 pi f d, which we have already calculated, and f d is the Doppler frequency shift, and so for this f d will be equal to 2 Vr upon lambda, and it is again changed to in the terms of our electromagnetic signal. 2 lambda has been replaced with C upon Ft into Vr. The radar frequency is Ft and it is equal to C bar upon lambda, and lambda is basically the wavelength at which the signal is coming out of the radar. C is the velocity of the light and Vr is the velocity of the moving target and the direction of line of sight of radar. So, these are the basic equations which are implied in the case of our radar when the Doppler shift is applied to it. Now, we comes to the simple CW radar. CW stands for the continuous wave radar, and this is the simplest block diagram of that. So, what is the what are the different blocks which are associated with the CW radar, that is continuous wave radar. So, here we are seeing that our moving object is coming towards, and here it is the antenna. We are sending a signal of F0 to it. The radar is, this is basically depicting the F0 is basically depicting the signal which is going towards the target from the radar. So, radar is sending a signal of F0 to the radar, and after striking the radar target, the signal will come back. We already know about this is the basic function of a radar. So, in this process what will happen? F0 plus minus Fd. Fd stand for Doppler frequency. Already we have gone through the expression of that, that is Fd is the Doppler frequency shift. So, it will be either plus or minus. There is a significance of plus and minus here. We have F0 is equal to plus minus Fd. So, F0 is the signal which is going from the radar to the target and it is hitting the target, and Fd is the Doppler frequency. In between it is the terms of plus and minus. So, what is the significance of plus and minus here? Just have a look. So, a transmitter generates a continuous oscillation of frequency f0 which is radiated by the antenna and which hits the target. A portion of the radiated energy is intercepted by the target and is scattered. Some is in the direction of the radar where it is collected by the receiving antenna. The portion of the radiated energy which is falls on the target is intercepted by the target and is scattered. Some will be in the direction of the radar and which is further collected by the receiving antenna. If the target is moving with the velocity Vr, already we have discussed, relative to the radar, the received signal will be shifted in frequency from the transmitted frequency f0 by an amount of plus minus Fd, where Fd is our Doppler frequency shift. Already we have gone through the formula, so I am not going to describe. We are basically focusing on the significance of plus and minus. If plus sign implies if the distance between the target and radar is decreasing, if this is the radar and this is the target, if it is decreasing, the distance between these two is decreasing, that means in the first case the distance is this much, in the second case this much, this much. If the distance between the radar and the target is decreasing, that means the target is moving close to the radar, means when the received signal frequency is greater than the transmitted signal frequency. The negative sign implies the distance is increasing. This is the radar and this is the target. So, if the distance is increasing, then we have a negative sign. So, all of you now I think understand the significance of plus and minus in the figure shown. So, what is the basically now? This is the transmitter section which is generating the f0 signal. Now, this is the function here. Now, it is going to the target and it is coming back with the f0 plus minus Fd. Plus and minus have its significance. So, you have to know about it. Now, these signals are now get into the detector section which is also our mixer. The significance of detector already known to you, post detection and the pre-detection methods we have discussed already. And after this, the Fd signal. So, in the detector section we have Fd plus minus f0 plus minus Fd and the f0 mixes, and we are coming out with the Fd signal which is our Doppler frequency shift. And then it goes to the beat frequency amplifier which basically amplifies the signal, and then to the indicator which basically now analyze the signal which is received from the target. The received echo signal at the frequency plus f0 plus minus Fd enters the radar via the antenna, already known to you, and is heterodyne in the detector mixer with a portion of the transmitted signal which is f0 to produce the Doppler beat note of frequency Fd. That is why beat frequency amplifier. So, the signal which is coming up out of the detection section is Doppler beat note of frequency Fd. Signal Fd is lost in the process. The purpose of the Doppler amplifier is to eliminate echoes from the stationary target and to amplify the Doppler echo signal where it can operate at an indicating device. Now comes the MTI radar. So, this is basically a diagram of the MTI radar where we have an antenna here and second one is the duplexer. What is meant by the duplexer? Duplexer is basically an antenna which can act as a both transmitting and the receiving antenna. And in the case of a radar, we are required with the transmitting and the receiving antenna both. That is why the duplexer role is must here. Now, the other are the different components of the MTI radar. So, here comes the pulse modulator, power amplifier, mixer, shallow, mixer, coho, intermediate frequency amplifier, phase detector and to delay line. The last one is here is the delay line canceller. So, these are the basically different blocks of the MTI radar. So, duplexer, mixer, IF, phase, pulse, power amplifier to the duplexer, and here shallow, mixer, coho. So, these are basically different blocks of the MTI radar. Just have a look at the different parts in detail. If the phase of the local oscillator were to change significantly between pulses, a cancelled clutter residue can result at the output of the delay line canceller, which might mistaken for a missing moving target even though only clutter were present. So, what is written here that if the phase of the local oscillator were to change significantly, if the phase of this local oscillator which is used in the case of for combining with the signal coming from the radar to the with the local oscillator, if the phase keeps on changing of the local oscillator also, because we already know that the signal which is coming to the radar after hitting the moving target, there in that case also we have a change in the phase, because phase we have seen the change because it depends upon the R which is changing continuously in the case of a moving target. So, since the phase of the moving target is already changing, and if we keep on changing the phase of the local oscillator also, then in that case the clutter comes into existence and the target can be mistaken with the clutter in that case. So, to recognize the need of high stability, so there is a need of a high stability local oscillator. So, the local oscillator MTI receiver is called the STALO, which stands for stable local oscillator. Just have a look at this STALO. This is the stable local oscillator. And what is the significance of this? That in the case of a moving radar, the target in the case of a moving target, since the phase of the moving signal coming from the moving target is already changing, and for that purpose, so as to the radar does not confuse between the actual signal received from the target and between the clutter, we have to make a stable local oscillator. The unstable local oscillator in which the phase keeps on changing is not suitable for this type of signals. That is why STALO comes into existence, which provide a stable local oscillator. IF, that is intermediate frequency stage, is defined as the matched filter. Instead of an amplitude detector, there is a phase detector. I think now every one of you will be aware of the what is the significance of phase in this case as respect to amplitude. Amplitude you can definitely amplify with the case of an amplifier, but the phase detector is the most important factor because phase changes with the distance r and following the IF stage, and it is a following the IF stage there is a mixer like device that combines the received signal at IF and the reference signal. Reference signal is provided by the coho, so as to produce the difference between the received signal and the reference signal frequency. This difference is the Doppler frequency. So, what we have seen here, STALO signal is coming from the duplexer, that is basically the antenna, and the signal is coming from the our stable local oscillator in the this mixture. Signal coming from antenna, signal coming from local out mixed here, and it is going to the IF amplifier. In the IF amplifier, signal gives the signal to the phase detector, not the amplitude detector. We already know about the significance of that. And here the signal is coming from a reference signal is coming from the coho one block here, and it goes to the phase detector so as to produce the Doppler frequency. Coho stands for coherent oscillator, to signify that it is the reference signal that has the phase of the transmitted signal. Coherency with the transmitted signal is obtained by using the sum of the coho and the stallo signal as the input signal to the power amplifier. Thus, the transmitted frequency is the sum of the stallo frequency FL and the coho frequency FC. So, basically what we are saying that the coherency in the transmitted signal is obtained by using the sum of the coho and the stallo signal. The combination of the stallo and the coho, sometimes it is called the receiver exciter portion of the MTI radar. The output, now the output of the phase detector. Output of the phase input to the delay line canceller. The delay line canceller acts as a high pass filter so as to separate the Doppler shifted echo signal of a moving target from the unwanted echoes of the stationary clutter. So, this is the Doppler frequency and it goes into the delay line canceller basically. And it is used to differentiate between the signal which is coming from the moving target and the static clutter. And basically here is the stallo, and what we are saying that the signal which is going transmitted is basically the combined signal of the stallo and the coho, which is power amplified by the power amplifier, and it goes to the antenna for the transmission. So, what is the basically the MTI radar in detail? That the signal transmitted, which is a combination of coho and the stallo signal, and it goes to the target, hit the target, and after coming from the target it mixes here, then IF amplifier, intermediate frequency amplifier, then the phase detector FD is created, and then it goes to the delay line canceller. So, here comes the end of the MTI radar, continuous wave radar. So, thank you for attending today's class.